Uh, Hello. Uh, this is mm, a bit stressful moment for me because I wasn't planning initially to give this talk, but due to some circumstances, yes, I will have it. And we had this conversation with one of the speakers who said he will join the talk, he will come over to see. And we were discussing what else can you do, what is more interesting than attending this talk. Out of a plethora of things, I think scrubbing your left ear with your right hand's pinky finger might be more interesting. Or taking a paper cup and making a dinosaur out of it might also be quite quite high in the ranking. Nevertheless, I'm happy you've joined. Uh, there was supposed to be a talk about databases. So this is not about databases. This is about distributed systems. When a talk is about databases, about databases internal, it covers a lot of algorithms for storing, indexing data, which happens when you successfully persisted something. What we will be talking about is what needs to happen for you to successfully persist data in the distributed storage. So it'll be a little bit academic-ish, and a little bit not. So stay with me. Might be interesting. And first and foremost, this talk is not to encourage anybody to implement their own distributed system. It's not worth it. But it's about understanding how certain aspects of a distributed storage, distributed system work, so that whenever you happen to work with such a system, you understand what's inside, what's under the hood. My name is Jakub. I came from Poland, from Gdańsk. This is a joke I landed last year at GeeCON. I still find it funny. I'm still, not only me, waiting for be able to go to a beach to have a proper Czech kladinka. I think that's how you pronounce it. So please keep up, Czech. I want to live nearby. Obviously, the last formality, you can join Slido and ask questions, which I will sneak peek, and we will cover them as we talk. So we have distributed systems. So a collection of distinct processes which are spatially separated and which communicate with one another by exchanging messages. A definition from mid-70s. And this is not the first and not the last. It's not the last time when Leslie Lamport is being mentioned in this talk. Not a long paper, worth reading. Interesting thing. Nevertheless, what we'll be talking about is a system where a failure of one computer you didn't know even existed can render your own computer unusable. So we have more than a single node in our system. And we want to write something to one of the nodes, C, IP, some data, and we want to read it from a different node in such a way that it remembers its state. Somehow, magically, it passes over the data, so wherever I call, I get what I want. That's the distributed system. And we'll try to look into what we need to think about to build such. So there will be a couple of ingredients. Will be obviously something listening on port 8080 because it's Java. And we'll probably have a concurrent hash map and a little bit of magic, probably some sharks, and then this is going to be profit. Not that easy. So we'll cover a little bit an HTTP server, plain Java HTTP server if we manage, but we'll focus on a distributed store and what we need to think up front or what we need to organize to be able to persist or send some data to our system so that it magically appears on different physical machine that we want to call. So we'll have to manage the traffic, so get data in and out to a server, discover who else is participating in the party, then set up a cluster, then have some thoughts about how we distribute data around. Then we have to think about how we serialize the data, because we have some objects and we want to get it into bytes to send it over the network. And finally, as we are distributed, we need to understand what happens if more than a single node starts accepting data. And there might be some concurrency issue. So, quoting the classic, welcome to Jakub. The store. So we have those 3 nodes, which we mentioned at the beginning, node 1, 2, and 3, and that forms a cluster. And each and every node talks over HTTP with its external clients, and talks over the socket with one another. Why? Well, HTTP is far more convenient for external communication, think REST, and sockets, yeah, low level, a lot of unnecessary overhead, but, well, less unnecessary overhead, but much harder to implement. I won't get deeply into sockets, not the scope of this talk, so we create a socket. We can discuss whether it should be blocking, non-blocking, Java new I/O, old I/O. Quite a few jobs trying to fiddle it at the moment and improve it at the moment. But out of this very simple reading from a socket, I would like to point you to one thing. There's a little magic of the serialization. We are reading something from network, so we will have to convert a stream of bytes into something usable. We'll cover it in a second, not everything at once. But for now, we have something that starts to listen over the network and is able to send the data. But to be able to send and receive data, well, we can do it on our own, but it's like talking with yourself, not very interesting on the long term. So to be able to send and receive data, we need a few peers, we need others who will be recipients of what we are sending. So we need to find our peers. So we need to find who else is in the cluster and how else we can communicate. So we can do a very classic one. We can just set up a static node list. We can say, this is the list of the servers. These are IPs. These are ports. Just go and talk to these folks. Surprisingly, very effective in many situations, but that's not what we would like to focus on, because there are better ways. For example, when we deploy anything to AWS or we deploy anything to our Kubernetes cluster, we can say that there is a little bit of deployment context awareness in what we are deploying, and we can handle discovery dynamically from the context we are deploying. So if we know we are deploying to Kubernetes cluster, we can also always within the cluster resolve an API, and it will give us some information about the service we are deploying, its IP address, its ports, and so on and so forth, the deployment context. We can do the same with AWS. If we deploy as ECS, we have list tasks, describes tasks, and also each and every instance, each and every container we are deploying has some context metadata that can resolve AWS clients. So that helps us discover who else is at the party. We can obviously implement it on our own. We can do multicast, so we can just send out data to everybody and ask them to figure out what to do with this data. So we can send datagrams. So if we can send datagrams, we can broadcast where we are, and whoever wants to join the party joins the party. Very simplistic. We can send out the record, which is, hi, that's my name, that's a cluster, I am in, IP port, and then we can join a multicast group, which is a special subnetwork, where we can distribute datagrams, and all the participants within the group receive that. Very simple, but in fact very effective. For example, for discovery. That leads us to and then we can read the datagram to have the information. Who else is within the who else? What are the nodes declares that they are in the same cluster? That leads us to a situation that nodes know about each other. So each and every node has a list of other participants in the clusters, so we can start playing with data. So we actually have a cluster. So we actually have multiple nodes that start to talk to each other. But in this picture, there is a certain assumptions that hasn't been mentioned. So in this one, we have a certain topology. We have a node 2, which is in the middle, and everybody is talking with node 2. That's not exactly what I had on the previous slide, because there are different topologies, and yet we have to decide how we would like to talk to each other. So we can have a star, we can have a circular topology where there's where the traffic is going in circles, or we can have something like everybody is talking with everybody. The difference is, if we say node 2 is in center, we somehow have to be able to decide which node is the leader. And I don't want to do that, because leader election, in fact, is pretty cumbersome process and pretty cumbersome algorithm. So what I would like to do is, I would like to go to a leaderless approach. Everybody is talking with everybody, and just exchange data. Very simple to form a cluster. And obviously, this simplicity will bite us soon, but we'll get there. So we have this all-to-all topology. Number of nodes, each and every node knows about its peers and just sends data to one another, broadcasts. Not ideal, but we've set up a cluster. So now let's distribute data. So we can queue the changes that one of the nodes or any of the members is accumulating, and we just need to distribute across the cluster. We have a set of queues which stacks up operations, and whenever there is something in the inbox or in the outbox, we either start dispatching or start consuming. Again, very simplistic operation, but we can get data in and out. That's our process of thoughts. One problem at a time. But we, again, stumble what we already seen. Sending bytes, sending stream of bytes is easy. The devil is how to get something out of those bytes. So we get into serialization and deserialization. How the magic we mentioned, or I mentioned at the beginning, can be uncovered. So serialization. People can say, "Hey, that's in Java." Yeah, that's one of the answers. Not ideal, but yes, Java serialization turns object graph into a stream of bytes. Essentially, that's what it's supposed to do, and that's exactly what it does. Though it does it with a number of caveats, a number of things that are not ideal. It's pretty slow, pretty clunky. it's very fragile to changes in format of the file, very fragile to changes in the classes, making the serialized version pretty much unreadable at some points. And reading and writing the data for non-Java code is hard or even impossible. That's one of the takes for serialization, not very good. But what we are here for is to understand that not which serialization method is the best, rather acknowledging the fact that this process will happen and this process has its consequences. Joshua Bloch in Effective Java wrote that there is no reason to use Java serialization anymore when you build system from scratch. He mentions JSON as an alternative, which is very brave of him. But he also mentions protobufs, which is more reasonable. And then Brian Getz says that we can make serialization considerably simple and safer by narrowing the goals explicitly to reflect this reality. We should seek to support serialization of data, not objects. And that's where a lot of serialization implementation goes. They support data, not behavior, and in Java, we pretty much serialize everything. And if behavior changes, it impacts serialization of it can impact serialization of our data. Because with serialization, we effectively want to extract the state of our serialized form, decide on the form, how we want to serialize, whether it should be an array of bytes, whether it should be a JSON or whatever else. Should we version the serialized form? And again, there are approaches that say, yes, you can version your serialized data. And there are approaches that say, no, not interested. We have other means to make your serialized version backwards compatible, but we are not versioning because that's another problem to solve which we don't want to solve. And then finally decide how we're going to reconstruct the object. So simple magic line to deserialize an object comes with many flavors. And then decide how we want to encapsulate the object state. So quite a few decisions. What is really cool is for a hobby university project, yes, we can use Java serialization, but in real life, people are using more profound things like protobufs, which was mentioned by Joshua Bloch, Avro, which can be versioned, different distributed storages use different ways to serialize data. So this little magic comes with a lot of decisions we have to acknowledge. And then when we have the serialized data, we are coming to, I think, a hardest topic: how to manage the concurrency updates within our cluster. So we have a situation that we have those 3 nodes in all-to-all topology, and we have there's a moment in time when we have 2 concurrent operations. There are clients connected to 2 nodes, and they are performing put operations or change operations on more than a single node. And the question is, which operation should win? Or what should we do with that? Because at some point, we want our system to be able to consistently respond with a right data. So when values are stored across multiple servers, that's what we actually seen, there needs to be a way to know which values were stored before the other. Very simple definition, but this definition brings us, it's like 20 minutes of a talk about distributed system, and it's the first time I'm going to mention the CAP theorem. But that's the moment. We need to decide on what was the causality of data, what was the order of incoming changes, and then which change takes precedence, which change is more important, if any, and that's pretty much all about the concurrency control. In general, now we have to think about how to implement it. So when we talk about concurrency control and CAP theorem in general, we can say that we can have strong consistency. So we value consistency, and we want a situation that whenever any of the clients ask our cluster for data, the response is consistent between all the clients. That's very strong guarantee, very hard to achieve. And CAP theorem describes why it's hard. But then what we can have is we can have eventual consistency. So we can have a situation that eventually, at some point in time in the future, the state of the system, the responses that it's giving, will stabilize, will converge on the common value, that all the nodes agreed. But if we ask until that consistency is achieved, we can get old value, we can get the new value. There is no guarantee. Though there is a guarantee, we'll always get something. We'll always get a value. And depending on the system we are building, it's either acceptable for us or not acceptable for us. There's also a third type of consistency which is quite common and quite often can be seen in the systems we are working with. It's called accidental consistency, or sometimes permanent inconsistency. That's also happening, but we don't want to cover that for obvious reasons. So the strong consistency. We have a situation when we have 3 clients, and strong consistency is about after a successful write, the third swimline, whenever any of the clients return a certain value, the first swimline returns 2. All other clients and all the following reads from the same client or from the other clients must also return the same value. So that's pretty much what we have in databases, the classic databases. And that also means that, based on the CAP theorem, it's very hard to distribute this data if that's the guarantee we want to give. So now, all topology is very hard to achieve, because if we get something to the node A, node 1, and then at the same time to the node 3, and they are just chatting with each other, exchanging data, it's very hard to make a guarantee that will consistently return the same value. That's kind of a consequence of one of the decisions we made we made earlier. We didn't want to get a leader. We didn't want to get a single node that will manage the whole operation. Will keep this kind of the sequencer for all the sequence of all the data, the order of all the coming data. So it's very hard for us to guarantee a strong, consistent reads. A decision we made earlier on impacts just now. So that's we seem that we just didn't elect a leader, but the consequences are much harder. So we can't do that. We also don't want to permanent inconsistency for obvious reasons, so we want to focus on the eventual consistency. We want to go to a situation that at some point in time we'll get the right data. So we are talking about a situation that on the third swimline we are having a write, and that write is distributed among different members of our cluster, and the client on the second swimline is receiving the data successfully and it's returning the correct value, but the client on the first swimline hasn't yet caught up and is returning a non-value. any eventual consistent word, that's okay. That might happen. At least we are getting a value. Sometimes it's more important to get something than get the exactly right value. But we have to think about how we can get into a consistent state. What needs to happen for those nodes agree on what's the state. So we have our cluster. We have a bunch of operation queued up in each and every node, and they're exchanging it with the second node that didn't have this operation backlog, and the second node is trying to scratch its head, trying to figure out, so what should be the correct value? If I have two operations updating the same field, or I have two contradictory operations, what should I do? Is there anything I can do to have the right value? Yes, there are some algorithms to figure that out, and we'll sneak peek into them. So we are talking about this situation. We have an update on the third swim line. We have an update on the first swim line, and yes, what value should be returned by the second client? Again, Lamport. In distributed systems, it's sometimes impossible to say that one of two events occurred first. We have found that problem often arises because people are not fully aware of this fact and its implications. That's classical conversation you have with your non-technical product owner in a business system, where you say, well, I received the data, but I have now to persist it across multiple things and process it and so on. So even though I said, yes, I have this data, you might not be able to see it in your results, for example, depending on the system, for a couple of seconds, for a couple of minutes. If it's a bank, until next batch loading the next day, things happen. And there are ways to try to do it better. There is a whole pile of papers called concurrency control in distributed systems, on distributed databases. I'll not cover that because that's a lot of reading and a lot of math. But we can sneak peek into a few things. What we can think about is, can we try to do a global ordering of events that are coming? Is it really possible? Because if we somehow are able to say, this was first, this was second, that will solve all our problems. And if we can't, is there a way to figure out, are there some data types that gives us ability to resolve conflicts straight away? Yeah, that's what we'll look into. Let's start with clocks. Before you ask, using just timestamp for concurrency control is a very bad idea. I can leave it as a bold statement, unless somebody wants to argue. The clocks that are in our computers are drifting by design. If our computers get hot, if the graphic card on our computer gets hot, that might impact the quartz clock, and that measures time. And to some extreme, it can be, if the device is very small and it's getting very hot, it can be up to seconds or tens of seconds during a day. So quite a significant change if you want to talk about the distributed systems. We have in Java something called system current time in milliseconds. And to surprise of some people, this is not a monotonic. This is a wall clock. This is a clock that is synchronized over NTP protocol by our operating system. So it is possible that two consecutive reads from current time in millis, will show you a drift and clock working backwards. That's okay. Because then also in Java we have something called nanotime, which is a monotonic clock, but it's monotonic within the single JVM. So within a single server. So if you start comparing nanotime between two different servers, you can get really weird results. So no, time as an absolute thing is not a good way to decide on concurrency control. But this monotonic clock idea, or monotonic clock time, is something we'll go further. Because can times out be synchronized? Yes, I answered. Yes, they can, but again, synchronization of timeouts works only in local networks. We've been building systems that synchronize a number of devices over a local area network where the latency is minimal, and with the millisecond latency you can synchronize the clock up to a millisecond or not up to individual milliseconds. But then if you want to do it over a geographically distributed system, it's much harder. It's much harder because you have network latency and the latency just accumulates. So time synchronization of machines works when they are in a single collocated space. If not, what else we can do? So no one said that the synchronization on time, the clock we are looking at, has to be a timestamp. It can be a very logical thing. It can be a version or a value that allows us to order things in time. And this is more familiar for many people than they can assume, because when you have a Hibernate entity and you use annotation version, there was a call out that I will not use any annotations during the presentations. Yes, they are. When you use in Hibernate version annotation, it's nothing else like a logical clock. It's a version that is incremented within a single server, which is our database, because that's where it happens. And based on the version, we know that we had 2 concurrent updates, and something we are trying to update already has a new version. So Hibernate provides us a certain level of concurrency control, in case you didn't know. It's kind of a logical clock. Logical clock that allows us ordering of order of changes within our entity, but that happens on a single server. The question is, can we derive it into multiple servers? So in general, yes. If we have a master in our cluster, that's fairly easy because master manages that. But in our situation, our topology where we don't have a leader follower, we kind of shoot ourselves in the foot. So we have to think how we can do it better. When you take Leslie Lampert's paper about logical clocks very naively, you can implement something like this, where you have a clock, and whenever you tick, so whenever you request a new value, you compare what was the latest you have with what's the requested, increment it, and return. So you kind of order your ticks. So you have all the other things around that request the tick, and based on that, you're able to figure out whether what you're writing is already the latest, or you're trying to write something, or you're trying to update something that you don't have the latest version of. And that's exactly what Hibernate did. When you try to update, they checked the version and failed if the version didn't mismatch. Hibernate was very ruthless in its handling the concurrent updates, but it had some ways to figure out that the concurrent update is happening. The ruthlessness was about go and figure it out yourself, I'll just throw you an error. But we can try to do better. In a distributed world where we have more than one server, there is a concept, there is a generalization of a Lamport clock or a logical clock called the vector clock, where we hold a vector of nodes that we're ticking, and based on that, we can figure out, so we have a map of nodes that were participating in our cluster, and based on that, we can figure out what is the version. It might look like this. So we have something on node 1 and something on node 2, and they are trying to create a new record. So clearly a concurrent update, and node 2 have to figure out what version is the latest one. So if we have a vector clock, we can try to figure out that we have node 1 with version 2 and node 3 with version 1, and that's newer, that's greater than node 1 with version 1 and node 1 with version 1. So we are able to say, okay, this is newer, this is more up-to-date value than the other one. And also the other way around. We can figure out that something is concurrent. We have node 1 with version 2, and then on the other hand, node 3 with version 2. So something happened concurrently, and we try to reconcile this data. We know that it's a problem. And also, we can have a new node, and we also know that it is a newer version. So there is a way for us to figure out some optimistic logging scenarios. So we optimistically assume that there are no concurrent updates, and if they happen, we have a certain way to figure out which comes first across a number of servers. That narrows the scope of problems and failures even more. So the question we are left with now is, can we automatically merge two data structures which were updated concurrently? Are there any data structures that can help us or that can aid merging when there are two different versions? Again, Hibernate says, hey client, you're smart enough to decide. I have no idea what to choose. But there are some situations where we can use a data structure that will help us with that, also depending on the system. So it's called conflict-free replicated data types, and it's a family of data structures like sets, maps, lists, counters, and so on that can be concurrently edited by multiple users or multiple servers. There is a way embedded in those data types to figure out conflicts in a sensible way. The principle underneath all the CRDTs, so conflict-free replicated data types, is that they must allow out-of-order merge operations, which still end up in a correct value. We can kind of build up a test, a classic mathematic proof of that, and there is independency that we don't need to care about potential duplicates that are sent from the replication layers. And there's a number of data types or algorithms that can help us, as long as what we are storing is within the scope of those examples. We can be pretty safe that, for example, if we have only growing counter, that we can resolve conflicts. If we can have only set when we are adding data, yes, we can resolve conflict. When we just scratch our heads and think a little, that's quite obvious. That's quite natural. We can have set that we can remove data, but we can remove only once. Well, we can remove only. We are not able to remove the same thing multiple times, so we cannot re-add things to a list, because that will lead to conflicts. So that will gives us some ways to figure out that we have a concurrent update. We know that, and depending what data we are storing, we can decide what to do. Another good thing, and that's why Hibernate is throwing an error at us, is that a human being, a client, knows much better if out of two data we are having, one is more important than the other, and can decide. That's why very often we have a human operator in this process that helps us resolving this conflict, obviously depending on the application, on the type of application. And then there is this ruthless way of resolving conflicts, which I haven't yet mentioned, but also among conflict-free replicated data types, there is last write wins, which means, hey, I have a concurrent update. I'll just pick one of those based on an algorithm I've implemented and remove the other one. So we want to get into a stable state because conflict is an unstable state. But we don't really want to care about the other value. And to some surprises, there are databases that works exactly the same way. They kind of defer the moment of conflict through different means, as we walked through. As I've showed, we can try to figure out if there is a conflict, try to order things in certain ways, but it's not solving a problem, it's deferring the problem further and further and further in time. But still the problem might arise, and then we just take the last one. And it's okay. Sometimes it's okay. There is a couple of databases. There's a database called Voldemort that uses version vector, so it's not like I've talking about some academic bullshit in here. There is React database that also uses version vector for the cluster and also supports last write wins conflict resolutions. And there is Cassandra, who is also using the last write wins. So we kind of work through distributed stores. I really hope that now whenever you stumble across an idea of, oh, this is a distributed thing, I'll do it myself, you won't. If that's the only takeaway from this session, please don't implement it yourself. Life is so beautiful. You can scratch your left ear with your right hand pinky finger. It's still better. We have a couple of more minutes. I don't want to talk about implementing HTTP server because it's not worth it at the moment. There's a couple of things which we haven't covered, like changes in the cluster topology. We just discovered clusters. We just discovered nodes form a cluster, and it's never changed. None of the members left the cluster. But it's an important thing because all of a sudden, your peer just disappeared, and you don't know if it disappeared and it will come back, or you just disappeared and it's gone. And what about the data? We didn't really cover ways for the cluster to figure out if other members are alive. That's also quite an important topic. Not talking about things like split brains that the connection breaks and you have two clusters out of one cluster and they have their own states and somehow you have to merge it again, which is a very hard topic in itself. And few other things, and many other things. You can have a look into those or read more about it. It's a wonderful book. I don't know why I said wonderful. It's a very good book. It's not as good as Winnie the Pooh, but it's very interesting and worth reading. Designing data-intensive applications. It describes pretty much all I've said, and then much, much more. And I think it leaves also with this takeaway that if you want to do it, please don't. If you want to do it at home, you shouldn't. If you want to do it yourself, please don't. You probably won't smart as anybody. You can do it as a pet project to understand things, but there's a lot of trade-offs you have to understand. And unless you're aiming for hundreds of thousands of concurrent writes, surprisingly, Postgres is probably good enough for you. Yeah, thank you. If I manage that, yes. Does your design has a guarantee of forward progress? That's a tricky question. I don't have an answer for that. Probably because I don't exactly understand what's under the forward progress. And by design, my design has no guarantees. It was a pet project for me to understand certain steps that are underneath. Is there some ways to prevent split brain situation when we have only even number of nodes clusters? What we have 2 nodes? So I don't think any distributed system that is supposed to be have any failover guarantees can survive with 2 nodes. Everything I can remember has an odd number of nodes, at least 3. Can we prevent split brain? No, because that's essentially coming from fallacies of distributed computing. Network is unreliable, and sooner or later we will have a network failure, which can lead us to separation between the nodes. I know from my experience at Hazelcast some years ago that there are people much smarter than me trying to prevent it or recover from split brains. And they had literally brain melt out of that. Brain split, yes. And it's tricky in many ways. I'm not an expert in that matter, and I probably am not able to give you a very detailed answer. Maybe at some point in the future. Thank you very much. So as I said, this was supposed to be run differently. I have one more talk as a lightning talk, totally different subject about JSON, much or far less complex. So if you want to join, it's the last session. It's a quickie. So I'll just torture you for 15 minutes, not for nearly an hour. Thank you very much, and enjoy the rest of the conference.